to have Professor Mike Strickland here in our seminar today. He just told me that he has been elected chair of the physics department at Kent State University. He's also the vice director of the Center for Nuclear Research there. He received his PhD from Duke University in '97, and then he taught and worked at Ohio State, University of Washington, Duke University, Technical University of Vienna, Helsinki University, Frankfurt Institute of Advanced Studies, and Gettysburg College before he finally came home to Ohio. He has published several books, 3 volumes of relativistic quantum field theory, and already as a graduate student, a book on neural networks together with Bernd Miller and Joachim Reinhardt. He works in nuclear and high energy theory, in astroparticle physics, and in atomic physics. And he is most well known for his work on high order calculations of the QCD equation of state using resummed hot thermal loop effective theory, and his work on anisotropic hydrodynamics, which he will talk about today. So it's with great pleasure that I welcome you, Mike, and the floor is yours.
Okay, thanks, Uli. So my goal for today is to try to give you an overview of the development of the anisotropic hydrodynamics program and a little bit of an update on what's going on these days, because we've been a little bit quiet down here in Kent. All right, so let's see if I can go forward slide. Good. So what's the motivation? Well, we know that viscous hydrodynamics is a sort of workhorse in heavy ion phenomenology, and it's quite successful over a broad range of energies, system sizes, and so on. But if you look under the hood, you'll see that actually it's being applied in a rather extreme environment, because we're taking 2 nuclei and slamming them at the speed of light, and the matter that's created in the wake of this collision is quite far from equilibrium. But typically the derivations of viscous hydrodynamics rely on a sort of near equilibrium assumption, together with a kind of Taylor expansion around equilibrium. The reason that you get driven out of equilibrium is because of the setup that I said. You take 2 nuclei and you slam it at the speed of light along one direction, and the tube of plasma that you create is expanding very rapidly along the longitudinal direction. And because of this rapid longitudinal expansion, relative to the transverse expansion, you see that the longitudinal pressure will be much less than the transverse pressure as tau goes to 0 plus, right, to the initial time. The largest non-equilibrium corrections, as I just said, occur at these early times. But if you also start looking near the edges of the plasma, you'll also see that there's also quite large non-equilibrium deviations. If you go from lead-lead to small systems, as I'll show you in the course of the talk, then the non-equilibrium corrections can be large at all times. And then you start to get really worried. And that sets up the goal of anisotropic hydrodynamics, which is to provide a kind of optimized hydrodynamic framework where we can describe not only the bulk of the matter, but also what's going on at very early times and what's going on near the transverse edges in a sort of controlled manner. Okay, before I describe anisotropic hydrodynamics, I have to go through what is viscous hydrodynamics, because it builds upon our knowledge of dissipative hydrodynamics. And if we want to understand viscous hydrodynamics, we have to take one step back and remind ourselves what is ideal hydrodynamics. In ideal hydrodynamics, you start from assumptions, basically that the system is in perfect isotropic equilibrium. And if that's the case, then the energy momentum tensor has to be expressible in terms of 2 non-trivial tensor products. In this case, a bilinear formed from the fluid 4 velocity that has, in the end, the components mu nu and the metric tensor itself. Now, in general, these coefficients that are sitting out here, A and B, are Lorentz invariant things that are frame independent. You can fix them physically. Here I've expanded this one as E plus P and this one is P by comparing to what you would expect to see in the local rest frame. And if this thing was in perfect isotropic equilibrium, you would simply have the energy density in the 0, 0 component and the same pressure along each of the directions. This is XX, YY, and ZZ. Those would correspond to the pressures in the three directions in our coordinate system. Good. All right, so in ideal hydrodynamics, as I wrote here, you always assume that you're in this form. And then once you assume this form, you can then get your equations of motion simply by requiring energy momentum conservation. So this equation is familiar with everyone in the audience. It contains four equations here, depending on whether you choose nu as 0, 1, 2, 3. There are 5 independent degrees of freedom in these equations, which are the energy density, the pressure, and the 3 independent components of the fluid velocity. Because this is always normalized to 1, there's only 3 independent components. So we have 4 equations and 5 unknowns. So we have to add an additional piece of information, which is provided by the equation of state, which can be expressed as some formula that must be obeyed by the trace of the energy momentum tensor. And this, in practice, is implemented by encoding, the pressure as a function of the energy density. So we eliminate one of these degrees of freedom by writing the pressure in terms of the energy density. Now, near equilibrium, this kind of makes sense. We can identify what is the equilibrium pressure and energy density, and then we can go do some lattice calculation of the pressure. That's the points that are sitting here, and then from that, also extracting the energy density, you can get this function. P is a function of E. So this step, the last equation here, is a sort of phenomenological input, if you like, that comes from lattice. But it's first principles, because if you have a big enough computer and wait long enough, you can beat this problem to death and determine uniquely what is the equation of state. Now, these 4 equations, if you project them with the 4 velocity and the components transverse to the 4 velocity, result in a set of partial differential equations. This capital D here is what's called the co-moving derivative. It's the normal partial derivative projected along the direction of the fluid 4 velocity. And another quantity appears, which we're going to see in a few slides. So I thought we should introduce it. Is this quantity theta, which is the 4 divergence of the fluid flow itself. So these, the first equation describes how the energy density responds to these gradients encoded in theta. This one tells us how the fluid velocity responds to the resulting pressure gradients. And these 4 equations, and in the end, supplemented by the equation of state, are enough to solve the ideal equations of motion. Now, of course, nothing in the world is ideal. And in perfect thermal equilibrium. So we might consider the following kind of expansion: that we take our full energy momentum tensor, we approximate it at leading order by some ideal, perfectly isotropic piece, and then we add some presumably small correction, at least if we're in equilibrium. Of course, this statement is general. I can always decompose T mu nu in this form, but usually when people are thinking about this, they're thinking that this is some small correction to the ideal contribution. And if you add this, and of course just do d mu t mu nu on this, you'll get similar 4 equations, except for now there'll be new terms that contain this tensor pi mu nu, which is encoding the non-equilibrium part. It will enter into the energy density evolution and also the flow velocity evolution. Now this tensor, being a symmetric rank 2 tensor, it has to be, because it's contributing to T, it has to be symmetric. We can decompose this tensor into a traceless part and a traceful part. Mathematically, that is done by applying some complicated angle brackets projector in order to get the symmetric and traceless part. And if we project out that part, we get what's called little pi mu nu, is the shear correction. And if you look at what kind of velocity profiles would give you a non-vanishing shear correction, you'll find that there are ones where you have some anisotropy in the system, in the sense that you have some ensemble of particles going one way and another, and that results in a kind of non-zero term here. The proportionality constant is this thing that we've seen in heavy ions a lot, the shear viscosity itself. If we look at the traceful part, then it's proportional. In this case, this is the 3 spatial derivative, it's not theta itself. This is a 3 spatial derivative of the fluid 4 velocity. And so it corresponds to sort of uniform compressions and expansions of the system. And it comes with its own coefficient here, which we call the bulk viscosity. Now, of course, if we have these additional terms in our equations of motion, we may not have enough information from just these 4 equations to complete the evolution. So we don't know, for example, how pi will evolve in time. Before I show you typical second-order viscous hydrodynamic equations, I wanted to first have one slide discussing this connection from this expression on the previous slide, if I can go back, and small deviations from equilibrium in a kinetic theory framework. So we look at this picture from a kinetic theory framework. We could take the one particle distribution function and write it in the following linearized form as some equilibrium piece plus some unspecified correction here I call delta F. And if I were to plug this in to the definition of T mu nu in kinetic theory, the first term, if I integrate this times P mu P nu over the invariant phase space, I get just the ideal part. If I look at this correction that's sitting here, I get a contribution like this. And so by comparing this to the previous expression, which was of this form generally, we can see that we now have a kind of kinetic theory understanding of what this pi mu nu really is. And that's the double-lined box on the right here. It's related to these deviations from equilibrium. So the farther I go from equilibrium, the larger pi mu nu is going to be. Now, if you expand in kinetic theory, at least, your derivation to nth order in gradients of this correction, delta F, then you'll get what's called nth order viscous hydrodynamics. If you stop at first order in gradients, you get what are known as the relativistic Navier-Stokes equations. And these go back a long time and I believe can even be found in Landau's text. The problem with stopping at first order is that you get a parabolic set of differential equations and they're acausal. So you probably want to go beyond first order. If you go to second order, you find that you fix the causality problem, you get hyperbolic differential equations that can now be solved, at least for it, they're causal for some range of the transport parameters. If I start playing too much with the relaxation times and E over S, there are possibilities that you can drive these into acausal regions. But in most of the applications that people do, this completely fixes the causality problem. The resulting equations of motion take for pi, and I don't show the case of the bulk. This is just the shear correction, and these are the equations that were obtained by Bayer, Romachka, Sun, Starnitz, and Schiff, as I recall, back in 2007. And we got an additional term here in this equation, which I've collected into the square brackets, a set of terms rather, that are all proportional to some new scale, which is called the relaxation time. And if I were to have truncated a leading order in the derivative, the gradient expansion, none of this would have appeared, and I would have just got the Navier-Stokes solution that pi mu nu is just related to this this eta over here. To the particular derivative over here. But the moment I have a non-zero tau pi, that makes these equations causal. If you compute what that time scale is, and this is just a rough estimate taken from just taking tau pi from the relaxation time approximation and plug in typical entropies and temperatures that you expect in heavy ion collisions, you find that this tau pi is on the order of 0.1 to 0.4 Fermi over C, depending on the value of eta that you put here, of course. What it tells us is that if we solve this, these set of equations coupled to the d mu t mu nu is equal to 0, we will find that after a few multiples of this time, that the solution will start to look like the Navier-Stokes solution. But if we start to go inside of the first Fermi over C of the QGP's lifetime, then this term becomes super important, and we need to take it into account. Good. Now, in practice, people solve these equations, so numerically. So you have some equation like this. I don't show you the equation for the bulk, but there's an analogous differential equation that's obeyed by the bulk correction, together with these equations that these that you have to solve for the evolution of the energy momentum tensor itself. So you can solve those numerically on a computer, and then the question becomes, how do I know that the sequence of approximations that I just made is reliable, and I can trust the output of the code? That's kind of a physics question. The code may be stable and run, but should I trust the output of the code? And the two quantities that people look at when trying to assess how far from equilibrium we are in a particular hydrodynamic evolution are a quantity called the Knudsen number, which is the microscopic ratio between the relaxation time on the microscopic scale and the relaxation time on the macroscopic scale. The microscopic relaxation time is this tau pi here, and the macroscopic relaxation scale is related to this the magnitude of these gradients of the forward divergence of the flow velocity. So if there's very, very large gradients, then the Knudsen number is large. And if tau pi is large, the Knudsen number is large. So those are the two cases where you should be worried. Now, if you can compute this from the code simply by evolving, all the fields, and in particular you can take the forward divergence of it here, and then you can calculate the evolution of the Knudsen number. To give you some intuition for this, if I were to ignore the transverse expansion and go in the very high energy limit where this would be approximated by Bjorken evolution, you find that the Knudsen number associated with the shear corrections goes like this: relaxation time for shear relaxation divided by tau. So the earlier and earlier I go towards tau is equal to 0, the larger and larger this number is going to become, and therefore I have super large gradients. I might be worried. You can also associate a Knudsen number with the bulk corrections, and that's related to the relaxation time scale for the bulk. But you also find in this case that this also diverges like 1/tau as you go to 0. Now, these are the gradients. What will happen is that the gradients will drive a large non-equilibrium response in the system if they are large. What that means in practice is that the magnitude of the components of the shear tensor will start to increase relative to the ideal contributions. The measure of this that we use in the simulations is something called the inverse Reynolds number. And you can construct it in a Lorentz invariant way by simply taking the full tensor product, in this case for the shear inverse Reynolds number between the shear tensor and itself, take a square root, and then scale it by the isotropic equilibrium pressure in order to get some dimensionless number. Now, the reason this number is relevant is because at least the space-like components of pi, they are corrections to the pressures in the system. And if those corrections to the pressure start to get large compared to the isotropic pressure, you should start worrying that this Taylor expansion that you made around equilibrium, where you assumed that pi's were small, that might be breaking down. Now, in the case of the bulk viscosity, it's simpler because it's just a scalar degree of freedom. You just take the magnitude of capital pi, which is this bulk viscous correction, and that gives you the inverse Reynolds numbers associated with bulk viscous corrections.
Mike,
yes.
I don't know whether you said it, but this pi is the same as phi that you introduced.
Yeah, sorry, this pi is the same as phi. Yeah, it's bad notation. I was thinking about it this morning, but I called it phi here because I had used capital pi up here for the full, and I didn't want people to get confused, but it led to another confusion. Thank you. This is what I called capital phi before. Yeah. Thank you. Good. So we can monitor the evolution of these quantities from a given hydro run. So here's a hydro run with a three-dimensional hydro code. This is taking just a slice in the XY plane. The left column shows you what happens if you evolve with the ideal hydro equations. The middle one shows you what happens if you include only shear, and the right is what happens if you include shear and bulk. And by just looking at these pretty figures, you wouldn't be able to know if I should trust the simulation or not. It gets me some results, they expand, I can see that there's an effect of the transport coefficients, but should I trust it? So you can take these same simulations and then extract the Knudsen number, the inverse Reynolds number from these simulations. If you do that, this is what you get in practice, and those are those same events that I showed on the previous slide. On the left is the inverse Reynolds number for the shear, and on the right top is the inverse Reynolds number for the bulk. Let's focus on this panel first. In this case, what I've done is just take a slice here along y is equal to 0 and then plot the time evolution in this color coding, where the color coding is telling us the magnitude of this inverse Reynolds number. So, and you can think of that as roughly the magnitude of the shear corrections, right? And what else is going on in this figure? There are two lines drawn here, a white one here at a temperature of 200 MeV. That's a typical freeze-out surface that you might extract from a fluctuating hydro run if you were to freeze out at 200. And then the white is if you were to freeze out at 100. Of course, people typically freeze out somewhere in between here. These are just sort of bounding this region for us. In terms of the color coding, what we see is that at very early times, this inverse Reynolds number is quite large. In fact, there's black-red regions here if we go out to these wings that could be particularly worrisome. And if we were to extend this figure, we would see that out here in the dilute region, this inverse Reynolds number remains large basically at all times. Now, this may not be particularly important because out here the matter is very dilute and already outside of the freeze-out hypersurface. But in practice, what you have to do is add kind of regulators to your code to regulate pi mu nu, and at least in normal viscous hydro applications. And anytime you have to introduce a regulator, it starts to worry you. After roughly 2 Fermi over C, we see that we start to get into this nice blue region, and blue means we're getting closer and closer to equilibrium. The darker blue we go here, and by the time we get into this sort of region where we do the freeze out, everything's sort of in this light shaded region. So we might trust that if we're going to do freeze out here, we can use these sort of linearized forms for delta F in order to convert the fluid into particles. So that's good news. That's why I wrote at the top of the slide, for lead, don't worry, be happy. Now, if you look on the right, this is the inverse Reynolds number associated with the bulk viscous corrections. In the center of the fireball, it's always small until you get too close to the phase transition temperature. And there you see this inverse Reynolds number rise very rapidly. That's related to the fact that in this simulation and many, there's a peak encoded in zeta over S as you get near the phase transition. So this, the fact that you see green here is related to that peak in the bulk viscosity itself. Now, of course, that is restricted to this region, and if I remove where the peak in my bulk viscosity is, I can move this curve, this little green region rather up and down. Probably in practice, you want to stay away from the green region when you're doing freeze out, because that will be a place where probably this linearization would fail. And once you get over here and like into this region, probably you're all right. The bottom is, I don't have time to explain the full math behind this, but what this is showing is the deviations from second order viscous hydrodynamics. That's what we call R2 here. And so red is when we expect there to be large corrections to the equations that we're using. In this case, for the shear evolution and the bulk evolution. And what you're seeing in these red regions is the time it takes for it to essentially reach the Navier-Stokes solution as we go forward in time. So once we get up here, this thing going to zero is sort of telling us that we're entering into the Navier-Stokes regime properly. Good. So this is relatively good news for heavy ions. As long as you stay away from this early region and you have some way of taking into account these non-equilibrium deviations, by the time you get to freeze out, you're all right. If you look instead at what happens in a PA collision, and this was a paper from Yemi and Denicol back in 2014, instead of plotting the inverse Reynolds number, they show the Knudsen number here. It's correlated with the inverse Reynolds number. So whenever you have a large Knudsen number, you're after a short amount of time, on the order of the relaxation time, roughly, you're going to get a very large inverse Reynolds number. So the two are correlated. And the color coding is red is bad, which I've indicated by this crying emoticon, and down here colors close to blue are good. And once again, they've indicated in this case two freeze-out hypersurfaces, one at 100 MeV and the white one at 180 MeV. So typically, again, we're freezing out somewhere in this region. Now, if you choose a lower,
the other way around, the upper one, the white one is 100 MeV.
This is 100. Sorry, thanks, Uli. This is 100. This is 180. Thank you. If you freeze out here, you might be very worried because the corrections to the linearized form for delta F might be quite large, but at early times you might be optimistic. However, if you start to put in more realistic features into the simulation, for example, if you allow there to be some temperature dependence of E over S so that it gets quite large at early times, you can also have quite large Knudsen numbers generated also at early times. And so there's only a little tiny window in this case where you would intuitively trust the equations, and out here you should be worried. And that's the setup for anisotropic hydrodynamics. We want a theory that's going to allow us to describe these early time deviations in terms of the inverse Reynolds number, and not to have to put in regulators at large R to take care of this stuff in anisotropic hydrodynamics. As we'll discuss, pi is bounded in such a way that the pressures of the system remain positive definite. And because pi is bounded in the beginning in the formalism, you never actually generate these large inverse Reynolds numbers that are seen here, and you don't need to implement regulators on pi. Good. So anisotropic hydrodynamics. How are we going to do better than that? That's the question. Well, as I said in the beginning of talk, what's driving those large corrections, at least at early times, is the fact that we've created the quark-gluon plasma in a very anisotropic manner. We took these two nuclei and slammed them together, and this little running animation is showing you them after they've collided, expanding away from one another. And as we can see here, at least at very early times, there is little to no transverse expansion, but there is this longitudinal expansion that's taking place at the speed of light, because these two nuclei are more or less moving at the speed of light away from one another. And if we think of this as a tiny little one-dimensionally expanding universe, we'll see that the momentum along the longitudinal direction will get redshifted relative to the ones in the transverse direction. Now, after some amount of time, the transverse expansion starts to kick in, and then you can start getting back to isotropy. But for roughly, the first 1 to 2 Fermi over C, there's no significant transverse expansion built up yet. The outcome of this is this cartoon, which I carry around, which is if you were to plot, because of this longitudinal redshifting, the longitudinal pressure in a local cell divided by the transverse pressure. So this is a statement yeah, as I said, it's a local statement about if I boost into the rest frame of one of the cells that in this fluid, I measure the longitudinal pressure, which is along the beamline direction, the transverse pressure, which is along the transverse direction. I can start with a variety of different initial conditions, going from something that might have more longitudinal pressure and would be a prolate distribution to something like a CGC initial condition that even has a negative pressure. Now, this is allowed in the CGC kind of framework because in CGC, you're not talking about particles, you're talking about fields. And if you build up a T mu nu from just electromagnetic fields, it's possible to have negative longitudinal pressures or negative pressures in general. And but as the fields basically cool off and condense into particles, if you like, at some point the pressures should be positive definite. But we find, and many people find, that it doesn't matter where you start from, you start here in this region that has very, very large pressure anisotropy. And in terms of the viscous degrees of freedom, very large pressure anisotropy means little pi is order 1 compared to the isotropic pressure. And then depending on where you are in this band, as you go forward in time, you will eventually approach nice isotropic equilibrium at very late times. How fast you approach it will depend primarily on 2 things. One is the magnitude of the shear viscosity itself. As we decrease the shear viscosity, we move up in this cartoon. If it was perfectly 0, right, that would be a bold assumption. Then this thing would stay at 1 the entire time, and there would be no little dip down here. The other way that I can move up here is by increasing the energy density. So as I move towards the center of the fireball, I move over here. Now, conversely, if I increase the shear viscosity, which means early times, if I had some temperature-dependent shear viscosity, that moves me down. If I'm on the edge of the plasma where the temperature is lower than in the center, that also moves me down. And that's telling us this intuition again that at very early times and near the edges of the plasma, we might be sitting on the bottom part of this curve instead of the top. If we're on the top where there's, let's say a 15-20% correction from nice perfect isotropic equilibrium, we can use our normal linearized formulas. But if we're sitting on the bottom, we might be concerned. Now, the place, as I noticed here, that you turn around from going from this, decreasing longitudinal pressure to now going back towards equilibrium, is the point physically at which this expansion rate that's going here balances with the isotropization rate via interaction. So there's, of course, these guys are scattering here, although they're being pulled out in the non-interacting case because of this sort of one-dimensional Hubble expansion. They can still scatter out of the longitudinal direction or out of the transverse direction and acquire longitudinal momentum. That's what happens here, right? That's how you start going back to equilibrium. But this feature that we have this large degree of momentum anisotropy at early times is universal. And I won't have time to talk about it today, but we can extract what's called hydrodynamic attractors, which will show you, no matter what initial condition you start with, what is the sort of universal curve that you tend towards. It looks like this cartoon. So how are we going to take into account this large viscous correction? So as I said before, in viscous hydrodynamics, the idea, at least if you come from a kinetic theory point of view, is that you take your one particle distribution function, you say to leading order, it's some nice isotropic thermal distribution function that's only described by a local temperature. And then I have some presumably small correction, which is called delta F here. Now, if the system is very far from equilibrium, let's say it was in this oblate configuration in the local reference frame, then this delta F might be quite large. So the idea is to sort of accept the fact that at early times, we're going to be in this highly anisotropic configuration. And the one that's most relevant is the one that I keep pointing to, the one with Cassia is greater than 0. At super early times, you can have this prolate distribution. But as I show here, what happens dynamically is you go to this attractor that has an oblate distribution. So the idea in the beginning, which goes back to 2 papers from Mauricio Martinez, who was my student, and then a postdoc, and then also Wojciech Florkowski and Radek Lubleski back in 2010. The idea was to look at this in a simple case. So we were just going to look at Bjorken expansion. So we just have one anisotropy potentially in the system, which is related to the correction to the longitudinal pressure. And the idea is that we're going to take some arbitrary anisotropic, some arbitrary distribution, which I call F aniso. This could be a Boltzmann distribution, Fermi-Dirac, Boltzmann, Bose-Einstein, you name it. And what I'm going to do is introduce some new parameter, which is this anisotropy parameter, which is encoding the ellipticity of the distribution in momentum space. When Kc is equal to 0, we have a nice perfectly isotropic distribution, and when Kc is in these ranges, we either have a prolate or an oblate. And the fundamental idea is that if I can incorporate this large correction into the leading order term, then if I were to perturb, of course, not everything is a nice spheroid either. Ideal would be the sphere. The leading order anisotropic hydrodynamics in 1D would be the spheroid. Everything's not a spheroid, so you need to add some corrections here, which we call delta F tilde. And you will find in practice that these delta F tilde corrections are much smaller than the ones that you would have gotten in a traditional approach, and that was shown in a paper with then graduate student Dennis Bazov and Uli and myself back in 2013. So there's a kind of systematic way where you can start from this assumption, and then by now dealing with these delta F tilde quantities, you can derive a new kind of hydro expansion around this ansatz instead of the isotropic equilibrium one. These there's another thing that appears here, which is lambda. You should think of that as the transverse temperature, and then Kc is this ellipticity. As I said, they are full fields that depend on proper time and spatial position. Now, in practice, the way that this has been done is we take this anisotropic form here, and we use what's called Strickland form. And that's just to take some arbitrary isotropic distribution. As I said earlier, it can be Bose-Einstein, Fermi-Dirac, or Boltzmann, and we stretch or squeeze it along one direction in momentum space. In this case, it's the PZ direction, and that's because this was designed for the Bjorken case. This parameter Kc can be physically related to the pressure anisotropy through the expectation value of PT squared divided by 2PL squared. So if the system was perfectly isotropic, this would be PX squared plus PY squared, which would be 2PZ squared, and then this would be 1, and Kc would be 0. But at the moment that we have any excess of or deficit of longitudinal pressure momentum relative to transverse, this thing is going to be a positive, and that's going to give us this oblate distribution over here. Good. So what's special about this form? Why choose this form? Well, of course, if I send Kc to 0, this will go back to being and I rename lambda to t, this goes back to our old ideal hydro limit. So if I assume Kc is 0, it's got the ideal hydro limit embedded in it. But it also turns out if you take not the ideal hydro limit, which would correspond to eta F over S goes to 0, but if you take the free streaming limit, so eta over S goes to infinity, you can solve the Boltzmann equation for in the free streaming case, and you'll find that the solution is exactly in this form, the Strickland form, but with this Kc parameter given by the following time evolution, at least for the Bjorken case. So this form allows us to cover the full limit from 8 over S goes to 0 to 8 over S goes to infinity. The other thing that this buys you is that F iso being a positive definite function, in this form, I can never generate a full viscous corrected distribution function that is negative. Now, this can occur in normal viscous hydrodynamics because this delta F term can be large and negative and be like bigger than FEQ, and then this can be negative, which is bad because it's supposed to be representing the probability of finding a particle at some point in phase space. If it goes negative, then things have badly broken. So in this case, what's going on here is that this is positive definite. It doesn't matter how large I make Cassie. I can make it, going to -1 limit or going to infinity. This will remain positive. So that's great. And it will also come back to be a great thing when we're doing freeze out, because if we freeze out from such a form, we don't have to worry about F going negative at freeze out either. The other nice thing about this form is that if you derive the aHydro equations from here and then linearize in this Cassie parameter, as I'll show you in a couple of slides, you can reproduce second order viscous hydrodynamics in the limit of small anisotropies. So second order viscous hydro is included as a sort of subset of this model. So I wanted to talk about that a little bit more and show you how you might connect in a simple case, for Bjorken flow at least, aHydro and viscous hydro. Good. So from a kinetic theory perspective, viscous hydrodynamics is understood as this dual expansion in the gradients and the inverse Reynolds number, which is the response to the gradients. The strict expansion in the Knudsen number, as it turns out, may not converge. However, by simply numerically solving the equations, you can resum all of these gradients in practice. Although it's a sort of formal issue that the gradient expansion might not converge if you start expanding it out analytically order by order, in practice, this part is relatively under control. But and aHydro does basically the same thing by just numerically solving the equations. What aHydro does differently is that it also resums an infinite number of terms in the inverse Reynolds number. So I wanted to show that to you on the next slide. So again, sticking to this simple case of Bjorken flow in 0+1 dimensions, we can introduce the shear correction. In this case, there's only one shear correction, so it's a scalar, which we call pi, and it's encoding the difference of the equilibrium pressure and the longitudinal pressure. So if it was equilibrium, of course, this thing goes to 0. Now, if I compute the longitudinal pressure in aHydro, what I get is an expression that looks like this. And I won't specify what these horrible functions here. There are some nonlinear functions that involve arctans and stuff hiding here, which we call the R functions. RL is the anisotropic correction to the longitudinal pressure, and R is related to the anisotropy correction to the energy density. And that's how you get this equation. So this little equation, which I called pi bar, is just pi over the local energy density. And now I have a map between the aHydro variable Cassie and this dimensionless variable, which is this normalized shear correction. And if I take this and plug it into the aHydro equations of motion and rewrite them, instead of being in terms of the evolution of Cassie and that transverse temperature scale lambda in terms of pi and the temperature, I can obtain what looks like a normal second order viscous hydro evolution equation. I have some time derivative of in this Bjorken case, that's the only derivative that can appear. And then I get some horrible term that's sitting here that contains yet another function. It's written in terms of these other horrible functions, but it's again some very nonlinear function that's sitting here. If you take this equation and then expand it around Cassie is equal to 0, so make a small Cassie expansion of this thing and this, which I call pi prime, you'll land in the bottom, which is sitting down here below. And this can just be done analytically with a piece of paper. And what you get out in the end is the DNMR equations. Now, in practice, we don't expand in small Cassie. So we solve an equation that looks like the one that's in the middle. And these two terms that are sitting here, this calligraphy H and pi here, they're essentially resumming terms that are all orders in this inverse Reynolds number. Remember, the inverse Reynolds number is related to this tensor contraction. In this simple case that we're in 0 plus 1 dimensions, this reduces just to the some number times the magnitude of pi bar. And to get the Denical equations, what I did was just take this and truncate it at some fixed order in C, and then we get this. But that truncation in C corresponds to a truncation in pi bar, formally speaking. And if we were to do aHydro, we could systematically include not only these terms that go through pi squared, but also pi cubed, pi 4, pi 5. They're all included in this equation. So this is why we say that aHydro performs this all orders resummation in the inverse Reynolds number. And as a consequence of this, if you evolve this equation in 0 plus 1d, you'll find that pi is in fact bounded in pi over epsilon. I don't remember the number. It's something like minus 1/3 to 2/3 or something. It's bounded, and that saves you a lot of trouble, because if it's bounded, then you don't have to worry about regulating it out in the wings and so on. And the boundedness of pi also results in having positive pressures, which is always a good thing.
Mike, you have 15 minutes left.
Good, I'm on time. Thank you. So that was the Bjorken case. What do you do in general? So in general, the idea is that we're going to do this deformation again. But now, instead of having only one anisotropy parameter, we're going to have an entire tensor of them. And because this is a symmetric rank 2 tensor, we can decompose it in the following way. Again, there will be some bilinear and u mu nu. We're going to introduce a traceless symmetric anisotropy tensor, which is sort of the analog of little pi mu nu from before. And then finally, this bulk term, which was, I either called it phi or capital pi scalar before. So this is a general mathematical statement that you can always decompose this rank 2 tensor into these forms. And then what we're going to do is evolve the components of this tensor. It's symmetric, traceless, rank 2, so it has 5 degrees of freedom hiding in it. U itself has 3 degrees of freedom. We have the bulk degree of freedom, that's a single scalar. Then we also have this temperature-like scale, which I've called lambda now, and little lambda instead of capital lambda. And then I have 1 degree of freedom also hiding in the chemical potential itself. And so there's 11 degrees of freedom hiding in this general form. And this form was first introduced back in 2012 by Maurizio Radek and myself, and then it was further fleshed out in these papers below. Now, just specifying the form of the distribution function isn't enough. We have to say how we're going to obtain our equations of motion. And for everything that's been done to date with aHydro, except for some important edge cases, which derived the equations from sort of anisotropic GR kind of setups, most of the work here has been done from kinetic theory. And one of the fundamental things that we faced in trying to turn this into a practical phenomenological tool is that we don't know anymore how to implement the equation of state, because the system can be very far from equilibrium, and these quantities that we're dealing with are always non-equilibrium quantities, unlike in viscous hydro, where the expressions for PEQ just naturally appear in the expression. So the method that we settled on was to use moments of what's called the quasi-particle Boltzmann equation. The quasi-particle Boltzmann equation is like the normal Boltzmann equation, where you just have a kind of free streaming term and collisional kernel. But now we're going to imagine in our heads that the particles that are comprising this kinetic system have temperature-dependent masses. if they have temperature dependent masses and there's some temperature gradient in the system, that means there's going to be some force on the particles. And that force is encoded in this second term here, which is related to spatial derivatives of this mass. So again, if there's spatial gradients of the temperature, there's going to be spatial gradients of the mass, and this term will turn on. So what we're going to do then is then take this temperature dependent mass and fit it to some lattice data. That's what I show you on the next slide. So what's shown in the upper right hand panel is the energy over the Stefan-Boltzmann limit and the pressure over the Stefan-Boltzmann limit as a function of T. These were the parameterizations that came from the Wuppertal-Budapest group. By constructing the entropy from these two curves, you can simply extract the temperature dependence of this mass scale. And I plotted here on a linear log scale. Up here at very high temperatures, we see that it starts to go flat, which means M is proportional to T, and that's consistent with what we expect in the high temperature quark-gluon plasma, namely that we have quasi-particles with masses that are proportional to the temperature. As we go down in temperature, we see visual indication of the phase transition, and then it's increasing very rapidly. That's because T is going to 0 while M remains finite down there. Now, one complication with introducing a temperature-dependent quasi-particle mass is if you just write down the thermodynamic quantities and start trying to take derivatives of them to calculate the pressure in say, two different ways from some derivative of the entropy or vice versa, you'll find that with a temperature-dependent quasi-particle mass, the thing is not thermodynamically consistent. So you have to add an additional contribution to the energy momentum tensor, which is this background contribution. You can think of it as kind of bag contribution. This thing is also depends on the temperature, just like M. But the requirement of thermodynamic consistency tells you exactly what this function B is. Once you've fixed M over T, you then solve some integral differential equation, as I recall, to obtain B. And now everything's fixed. So we know how to compute the full T mu nu. We know how to implement the equation of state, and it's done through these quasi-particle masses such that we reproduce exactly the lattice equation of state. The other thing, which is important, I'll go quickly because I'm a little bit short for time, just because I'm talking too much, is this question of freeze out, right? As I mentioned earlier, if you were to use second order viscous hydro, the typical approach, although people have been improving this in recent years, is to linearize the thing in the shear correction. And if this becomes large, you can find regions where F is negative. And this happens a lot in small collisions simulations. I believe the quote from Bjorn Schenke and the others was for P-lead, for example, it was like 40% of the freeze-out hypersurface cells have a negative F. So this is an issue. Now in aHydro, because this is a positive definite thing, we can just sample from this and it's always positive. We don't have to play any games. Now, is it really better? Before you start going to phenomenology, our plan was to look at exact solutions. So we constructed a set of exact solutions for Bjorken flow, for the RTA, for non-conformal Borken flow, for Gubser flow. And what we found, and I'll skip over a bunch of slides now, is that in all of these cases, aHydro performed the best when you confronted it with exact solutions. So I'm skipping over slides now. So given that it seems to work best in a variety of extreme situations, our next step was to apply it to phenomenology. And for the next few slides, what I'm going to show you is some old results and also ones that I won't show you the ones that came out in the last year, but all of these so far have been using smooth Glauber initial conditions. I'll come to fluctuating initial conditions in the last slide. We're going to use some wounded nucleon plus binary collision profiles with some particular mixing fraction. In the rapidity direction, we use tilted central plateau with Gaussian wings. where for what I'm going to show you, I just took the system to be initially isotropic in momentum space. Now you might worry what the effect of this is. Now, of course, our understanding now of the hydrodynamic attractor tells us even if you started isotropic, you're not going to remain isotropic very long, and you're going to approach this attractor thing. So I'm not too worried about this assumption. We run the code, and then we extract a freeze-out hypersurface, which is associated with the energy density in this case, so a fixed energy density hypersurface. We then sample from this, deformed aHydro distribution, now with 3 anisotropy parameters, 1 along the longitudinal and 2 along the transverse directions. And then we use something called Terminator 2 to, at least in the old papers, to take care of all the resonance feed downs. And this is the quality of the fits that we obtained back in 2017. The fits were done to these 2 centrality classes, 0 to 5% and 20 to 30. And the fit parameters at our disposal were the initial central temperature of the plasma at 0.25 Fermi over C, the shear viscosity to entropy ratio, and the freeze-out temperature. And the top shows what happens in 0 to 5 and the bottom into 20 to 30. And once we fit these 3 parameters, we could then describe the data in a variety of different centrality classes. For very central collisions, it seems to work remarkably well. As we get to more and more peripheral collisions, not surprisingly, it starts to break down here at very large PT, and that's because our quark-gluon plasma is very short-lived, and in fact, if we keep going up in the centrality, eventually we don't create a quark-gluon plasma at all. Once you see this, you know that you can integrate these spectra in order to get the average PT, and aHydro seems to, at least with smooth initial conditions, has a good description of this observable as well. The DN-data description is also very good. Now, part of this is tuning these Gaussian wings. So we did have some additional parameters at our disposal, which is when does the approximate boost invariance of the initial condition break down? That's the width of the central plateau, and there is some wings. So sort of the width here and the wings was another input parameter. But those weren't tuned to the spectra. Those were tuned to this kind of data. But once they were tuned, in one centrality class, you could then describe all centrality classes basically. Not only this, we can get elliptic flow out of the formalism. So this is V2 in a variety of different centrality classes. And this is the identified V2 for protons, kaons, and pions. Once again, if we restrict our attention in the low momentum region, it seems to work quite well. We can also extract HBT radii. What's shown here on the left is R out in different centrality classes, R side in different centrality classes in the center, and this is R long in the final panel. And we seem to have at least this was at 2.76 TeV, a reasonable description of this data. And if you take the ratios, it looks even better. Now, this was great because in essence, Terminator did this for you. We just had to learn how to just run Terminator. We didn't adjust any of the HBT code. We just ran it and produced these plots. And of course, there was some learning to do, but it worked reasonably well. So there's some other phenomenological results, which I have limited time today, so I didn't show them, but you can go and read these papers. And then finally, I wanted to tell you just on one slide, I don't have any results to show you today because it's a work in progress still, but what's happening now. So we've been working on creating and integrating what I'll call a standard stack of software for use in event-by-event simulations. And our idea was to try to standardize on what is a kind of community agreement. So right now, the code allows for modular implementation of different 3D fluctuating initial conditions. The user can select Monte Carlo Glauber, Trento, IP Glasma initial conditions, and just use them. The equation of state can be based either on Wuppertal Budapest or hot QCD now. The next step was that we got rid of our simple hypersurface finder, and now we use this code that was from Hannah Peterson and Ozzy Hulvanen called Cornelius. And then we use a code from Chun Chen, which is called ISS, to sample those. Now, this code has been modified to allow for these anisotropic aHydro distributions, and it's sampling from those instead of now viscous hydro distributions. The nice thing about using Chun Chen's ISS sampler is that the output can then be immediately fed to URQMD and or SMASH. So far, we've been testing everything with URQMD. All right. That brings me to my conclusions. So I tried to just give you a brief introduction to aHydro. What are the fundamental ideas behind it? Where is it going? It builds upon these advances in second order viscous hydro to try to push things into more extreme, let's say, regions of space and time. And we now have this running 3+1 dimensional ellipsoidal hydro code. What that means in practice is there's 3 different anisotropy parameters, and it has realistic equation of state, anisotropic freeze out, and now fluctuating initial conditions. What's happening in the moment is that we're running the fluctuating initial condition code, testing to make sure that everything is right, and then redoing our fits to data to try to extract, you know, in the case of Trento initial conditions, right? What's the magnitude of this normalization constant that you have on the fluctuating initial condition, and so on. And with that, I'll end. Thank you.
Thank you very much, Mike, for a very nice and pedagogical talk. We have a few questions accumulated in the chat, which I will call on first. But in the meantime, if you have additional questions, I see one hand up already. I'll take those after we go through those in the chat. So the first question is from somebody called Sleepy Fermion. If you could open your mic and repeat your question.
Yes. So we're trying to explain how you solve your Boltzmann equation, saying that you are using the quasi-particle picture and say that the particle masses are determined from the lattice data. So I think the purpose is to deal with the case, which is a little bit far from the equilibrium. But as far as I know, that lattice data can only give you the particle mass in equilibrium. So I just wonder that, is this true? Is my understanding true or not?
Yeah, so I mean, they can, we don't, this is not a direct extraction from the lattice. So it's not like they're measuring the Debye mass as a function of temperature, and that's this curve that we're using. In the quasi-particle model, they simply measure the energy density and pressure, and then we fit the entropy density by choosing this form of m over t.
Oh, okay. So you basically using this like free particles model to get the reproduce this entropy, which is calculated from the lattice data. Is it correct?
Yes, that's correct.
I actually have another question. So as far as I know that, for example, you talk about viscous hydro. In viscous hydro, you have like 2 transport coefficients, like shear viscosity and bulk viscosity. And in aHydro, you have also introduced another coefficient, which describe the let's say anisotropicity of the phase space distribution. Right. I wonder that you call it Cassie, right? Yeah. On one slide, you call it Cassie, and as far as I know, that all the transport coefficients C can be calculated in principle using some equations like Cooper formulas. I wonder, is there any way to determine this C from more macroscopic theory or not?
Yeah, I mean, I guess.
Hello, Sleepy Fermion, can you state your name and open your camera?
I do not have camera available now, so
Fine.
sorry. Yeah.
Who are you?
Fan.
Okay.
Yeah.
Yeah, so I guess conceptually, the confusion that you're having is you're thinking of Cassie as a transport coefficient. It's not a new transport coefficient. It really is a replacement in this case for pi, which is a dynamical degree of freedom. So Cassie is really a dynamical degree of freedom. You don't add additional transport coefficients in this case. Now, in the case of aHydro, when you start expanding it, actually, because you don't do this truncation, you in principle have an infinite number of transport coefficients floating around, but they all, if you start from this quasi-particle Boltzmann equation, there's a relation between them all. So it's not like you have an infinite uncertainty. They're all tied together in this case. So yeah, this is a dynamical degree of freedom. In the end, there's a one-to-one way that, at least in the 0+1, I can write down a simple formula that relates those two things. So you should think of Cassie as a sort of upgraded pi.
Okay, I see. Also, by solving some formula like this, you can just get Cassie from pi.
Yes.
Right.
Yeah. Or I can compute at any moment in time. If I know Cassie, I can get pi.
Yeah. But I mean, how? You do not have space to explain, maybe, but I just
it comes from this fundamental definition of pi, right? That it's just the difference between the pressures. And in this second term, I can just compute the pressure with this aHydro form that results in this term here. So
and you find it in his papers, the details.
Okay, I see. Thank you.
Yeah. Also in Uli's papers.
Okay, Travis Dorr has a question.
Hi, thanks for the really nice talk. I was wondering just a couple of things. One, why does it make sense to talk about quasi-particles in the strongly coupled regime, especially near the transition temperature?
Right. This is a bold assumption on our part, especially in this region, right around the phase transition. This is where this assumption is most suspect. If we go into the high temperature region, the lattice equation of state, at least at temperatures above, let's say 500 MeV, seems to be very well described by HTL perturbation theory. So we believe at temperatures above there that, a sort of quasi-particle picture applies. Now at super low temperatures, we know that there is another kind of quasi-particle that's relevant. It's called the pion. And we can write down transport equations in terms of hadronic degrees of freedom and pions, right?
Right. Yeah.
So the nature of the quasi-particles is changing from here to here, going from normal QGP-like ones to hadronic ones. You're right, in the transition region, we don't really know. And we've just made a bold assumption that we can just connect these two quasi-particle kind of descriptions.
And so along those same lines, all right, so when you're fitting, you had your later slides, like you were fitting all this data and everything, were you actually running hydrodynamic equations, or were you just solving moments of the Boltzmann equation?
Well, we have, all of our hydrodynamic equations are obtained from moments of the Boltzmann equation in this case. So it's the same, right?
Sure. Yeah. I just mean, like, if I go to DNMR, like I calculate an equation of motion for the moment, right? And there's a difference between doing that and going to kinetic theory and calculating the moment as a function of time in kinetic theory. So I'm asking you which one you do in practice, just because I'm wondering what kind of shear viscosity, for instance, you might get out of these simulations.
Right. So well, these are done at the level of sort of partial differential equations, which are equivalent of the hydrodynamic equations of motion. So there's a set of, in general, 11 partial differential equations that you solve, which describe the motion, the moments, right? It's not like we're doing a full Boltzmann simulation with the quasi-particle masses, because that would be too expensive in the end. Now you could just do it, but you would wait for your computers for a long time. You could just solve this, right? And then, as you said, start evaluating the moments, right?
Well, maybe the question was slightly different. I think if you start from kinetic theory and you write down equations for the moments, for the hydrodynamic moments, the structure of these equations are the same as the ones that you are solving. but the values of the transport coefficients would be constrained by kinetic theory, whereas in your case, some of these are used as fit parameters.
Right, that's correct.
Ah, okay. And so just along those lines, what kind of, I mean, does it even make sense to ask like what kind of shear viscosity you get out of these simulations? Because I'd be surprised if you got something like super small, right? Since it's all kinetic theory at the end of the day.
Well, I mean, from the fits, again,
Let's
as
just
we said, I could, yeah, I can in principle with self-consistently in the same model calculate E over S, right? And then, but we keep it as a free fit parameter, and this is the value we get, which is about 2 times the lower bound.
Okay.
Before I take Christopher's question, there is another one related to the same issue of quasi-particles by Szabolcs Barzani.
Yes, and thank Mike for this great talk. I wonder, you have so good agreement with data. Would it be possible to constrain the equation of state that you normally take from the lattice? If you didn't know what lattice gives you,
yeah,
would you be able to constrain it?
Maybe if I assumed that I had nice Bjorken, smooth Glauber initial conditions, that's what resulted in this. I could then try to extract. But once you start to do the fluctuating initial conditions, many people have gone through this exercise of trying to reverse engineer the equation of state from doing a kind of Bayesian analysis. And there, you get, I would say that although like the results from Scott Pratt and company, it looks like you can constrain the equation of state within some rather large band in these kind of fluctuating initial condition events. But yeah, you can in principle do this from a data-driven approach, yes. My understanding is that you won't be able to do it to any high degree of precision, though.
Yeah, or you need some other assumptions.
Yeah.
Okay, fine, thank you.
Okay.
Next question from Chris Blumberg.
Hi, Mike. Thank you, as always, for the very nice talk. I had a question, so I think it was sort of in the ballpark of slide 10. You motivated this aHydro formalism by looking at the study by Denicol and Naemi. Yeah, with the emoticons. Yeah, it's slide 12. So, so you see this really highly elongated structure in the isotherms and these isothermal contours in these PA collisions. And I don't remember if you showed it, but I might have missed it if you did. But I'm curious. So when you take the same set of initial conditions and plug it into aHydro, what do these isothermal contours look like in that case?
They'll look very similar. And the reason you get this really long stretch here is that in PA, you have a much smaller overlap, right? So you have a much larger transverse expansion. So that's why you see this curve going out super fast, right? In this direction is the transverse expansion. And what you get is a kind of shell in the middle that looks a lot like Goopser flow. In these events. So why the hypersurface is shaped like this, we kind of understand. And if I were to run aHydro and extract the hypersurface, it would look very similar to this.
Okay. I guess. Okay, that makes sense, because I guess the transverse dynamics is not so much affected. It's really the longitudinal component that gets resummed, like you were describing.
Right. Yeah. So we went through some comparisons back in the day between aHydro and normal viscous hydro, which here is encoded in DNMR. This is for Goopser flow, and yeah. So although qualitatively everybody's in agreement, quantitatively aHydro does best compared to the kinetic. But qualitatively you'll get the same picture. That's what I'm trying to say. If you look at either of these.
Just to clarify, Mike. Have you done PA collisions already? Have you simulated PA collisions?
I have internally, but I haven't presented them publicly.
And so you confirmed that you had this shape for the freeze-out.
Yes.
Okay. Yes, I think this takes care of the questions in the chat. I will now go to the list of raised hands. Huichao was first.
Hi, Mike. I think this is a nice talk. And I also found that you show nice agreement with the data for large system such as lead-lead collisions. And I think a traditional hydro always can always produce such results. But for a smaller system, I think traditional hydrodynamics actually fails. For example, to reproduce the data for PP collision, especially for the correct sign of C24. I'm wondering, do you think it's possible to solve such a C24 puzzle in the smaller system with this anisotropic hydro?
It's possible, but there is no guarantee that it will be solved. I mean, we're now running small systems and event by event. The reason I haven't released anything so far is that our agreement with the spectra in those cases, even for lead, when I turn on the fluctuating initial condition, is not as good as what we're seeing here. So I've been trying to understand for the last few months why that is. But yeah, this study is in the queue for the next 3 years. I've promised it to the DOE, so it will be done. Yeah, and I don't know if it'll solve the problem, but we're going to try and see if it makes any difference.
Yes, thanks.
Yeah.
Yeah. Next, Will Horowitz.
Hey, Mike. Thanks so much. Very nice talk, as always. So 2 questions, hopefully one quick and one maybe a little bit longer, if the chair allows. So the first question is with respect to the acausality of first order viscous hydrodynamics. And I was under the impression that George Noronha had thought that through and had figured out whatever it was that caused acausality. So I wonder if there's some update on that theoretical progress or not. And then the second question is, could you maybe talk a little bit more about the connection to lattice and the phenomenology, and in particular, so if we're looking at, say, small systems, might there be some kind of correction with respect to lattice, which is generally extrapolated out to infinite volume limits, and then lattice, which is also calculated when static, steady state, so on and so forth, compared to the much more complicated system that we consider in phenomenology? Thank you.
Okay, yeah, so to the first question, yeah, so George and Descanzi, and I guess also Pavel Kovtun and collaborators in the last years introduced a new kind of first order formalism that is causal at first order, right? And they've done this by basically going to a different hydrodynamic frame. Typically, these things are kind of formulated in Landau frame or Eckhart frame, and in that case, you have to go to second order in order to get the equations to be hyperbolic. Whereas in the case that George and Marcelo and Pavel have been talking about, in that frame, you can just solve a set of first order equations. Now, I'm not an expert in that. Maybe there are some experts in the audience. I'm still confused in that formalism how I put in initial conditions for my fields. Because they're first order equations, things like pi aren't independent degrees of freedom anymore, right? I don't have as many equations at my disposal. So it's not clear to me in that formalism how you would encode the non-equilibrium corrections. Now, I'm not saying it's wrong, it's just that I don't understand it. Now, it is possible, and people are looking at this. I think Derek, Tini, and George are working on trying to turn those into actual practical solvable equations that we can use to look at heavy ion phenomenology. I think it doesn't say that this was wrong. It's just that if there's a better frame, right, that you can work in, and there you don't need to go to second order to restore causality. I think that's their basic statement. Now, how that affects phenomenology, I don't know. I don't know. This is a simple answer. One could imagine trying to do a similar thing with aHydro, but and try to formulate it in the same frames that they're using. Nobody has done that yet. Does that answer the first? I want to discuss that before going to the second. So the second, now whether there are finite size effects when one starts making the system size smaller and smaller, whether there could be corrections to the pressure and the energy density, I would say the answer is yes, there might be, right? And I know that you and Alexander Rothkopf have recently started looking at this, and I think, as I understood your paper, and correct me if I'm wrong, they seem to be rather small, that I don't have to have the box size rather large in order to already get to the the large volume limit. Is that a fair read of your results?
Well, I think we don't have anything where we're anywhere close to QCD. So on the sort of the analytic side, we're dealing with scalars, and so how close to reality that is unclear, but it's suggestive. And then the lattice simulations, I think, are not at a state where we feel comfortable yet fully with them. So yeah, I mean, I wasn't trying to sort of just advertise my own work, but I do think it's just something that I've been worried about for quite a while.
I know. I share your concern. I share your concern, and I'm counting on you to solve the problem.
No, working on it. Working on it.
Okay, there's also some answers to questions that were raised by Travis in this chat, which you can read while I take Nu's question here.
Yeah, hi, Mike. Thank you for the very nice talk. I have a question, actually 2 questions on slide 31. Just go back to your calculation and compare to Ali's result. So you list the temperature here. Is this true that this temperature is the same for central collisions and the very peripheral beams as well?
Well, this temperature is the idealized one if it was a perfectly head-on collision and you were sitting in the center of the fireball. That's what this is.
No, I'm talking about this T freeze out, the lower one.
Oh yeah, I keep that fixed. I don't. Yeah.
I see. So in your calculation, you fix them. So
yeah,
I see. Now, okay, experimentally, we observe that just by analyzing spectra using blast wave, that actually we see there's a evolution, the lower temperature parameter and larger collective velocity and temperature increase towards the peripheral collision. So that's the observation both at LHC and the RHIC. So
yeah, one could imagine trying to turn this into a parameter you tune in every centrality band, but that we didn't want to do that. We wanted to keep this fixed across centralities. In principle, it should be an arbitrary switching point, and the results shouldn't be very sensitive to this if you've done your job right. I would, but in practice, we found that you did need to choose a specific value in order to get the best description of the data.
Right. Is it possible we get this data point of your calculation and then we analyze that?
Yeah, no problem.
Just for fun. So
yeah, but keep in mind it's Glauber initial conditions. It seems to work well, but it's not the most realistic.
You mean optical Glauber?
Yes, optical Glauber, not even Monte Carlo.
Next has to do with your last comment here. No chemical potentials. So could you comment on the high baryon density region for the RHIC B-scan phase 2 program, basically on the finite chemical potential region? Could you comment?
Yeah, I don't have any results to show you, but what I can tell you is that you can include finite chemical potentials here also in this underlying distribution function, and you can add an additional equation which comes from the 0th moment of the Boltzmann equation in order to get evolution equations for the chemical potential as well. There's no phenomenological papers on this yet. There's been sort of theory papers of how would you enforce fixed number density and things like that, but in this formalism, but it's in the works. So you can introduce the finite chemical potentials. What this means here is that I didn't introduce any baryonic chemical potentials on the freeze-out hypersurface, like a strangeness chemical potential or something like that, in order to fit the data. So I just assumed all of the fundamental chemical potentials were 0 here.
Yeah, understand. Yeah.
Yeah.
All right. Thank you.
No problem. Thank you.
Before I let Travis ask a second question, let me take chair's prerogative and ask a question myself. If you could go to slide 34. What version of V2 did you take from the experiments to compare your predictions to?
That's a good question. I don't remember. It's been too long.
Yeah, because this is Glauber initial conditions, so it lacks the effect from event by event fluctuations, whereas all the standard measures in the experiment are affected by event fluctuations. So maybe I can rephrase the question. Do you already have some unofficial news from your new studies, how that comparison works once you include the event by event fluctuations?
No, I don't have anything that I can tell you right now.
I'll be patient then.
Yeah, thanks.
Travis,
Sorry.
other shot here.
Sorry.
Thanks a lot for giving me the chance for the second question. I was just wondering, along the lines of a question that was just asked, in terms of the beam energy scan, at these lower energies, I guess intuitively I wouldn't expect the differential between the longitudinal and transverse pressure to be as great as it is at at these highest energies in LHC. So can you comment on why it still makes sense to talk about anisotropic hydrodynamics in these lower energy regimes?
Yeah, you're not going to be fully in the sort of Bjorken limit where you get complete pass through, and that's what generates this large longitudinal pressure anisotropy. How should I say it? Yeah, so at super low energies, you actually get the opposite. You'll get a prolate distribution because that's during the nuclear pass through, because most things have longitudinal momentum rather than transverse. And at super low energies, the picture flips on its head. And then instead of having aHydro with an oblate distribution, you have aHydro with a prolate distribution. And you could imagine applying it during the nuclear pass through when even this prolate distribution deformation is large. Now people have, I think there was a paper by Hannah looking at lower energy simulations where they just used URQMD or something, and they just tried to measure these pressure anisotropies. And my recollection from that paper is that there's not a strong dependence on the beam energy for these pressure anisotropies. Now, once you start looking at after the nuclei have passed through one another, you're going to have a less degree of pressure anisotropy after that than you would in a full energy heavy ion collision at LHC. But yeah, I don't know. I mean, it's a quantitative question, and the only way that we address a quantitative question is by running the code and see if it describes the data.
But there is nothing wrong with using anisotropic hydro, even if not standard viscous hydrodynamics would be okay, because then anisotropic hydro would just approach that limit automatically. You wouldn't have to do anything by hand.
Right. That's also true, right? Yeah. So if you imagine yourself applying viscous hydro, you might as well apply aHydro. Now, both could break, right? And then in the super low energy collisions, and then we have to do kinetic theory, for example, right?
All right, we are running up to our time limit, and also I don't see any more raised hands or comments in the chat. So I think this is a good time to thank Mike again.
Thank you, everyone.
And we'll see each other again next week. Any more words from the organizers?
Yeah, thank you, Michael, for a very nice presentation. Yeah, thank you.
Thank you,
Uli, for this last year. Yeah,
Uli, you're our organizer. Thank you, Mike.
Thank you.
Okay.
All right.
See you somewhere in the world.
Next week.
Hopefully in the real world, yeah.
Yeah, I'll be in Poland next week if you're going to be there.
Okay, see you.
See you.
Oh, hi, Akira. I haven't seen you in a long time.
Bye-bye.
Goodbye.
Goodbye.